Hey everyone, this is Mrs. Martin with today's notes on logarithms. I have a special affinity for logarithms because my bio teacher in high school, may he rest in peace, he was such an incredible man. And when he taught us logarithms, for whatever reason he was teaching us logarithms in bio, he comes marching into the room just yelling, log, 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 log.
What rolls downstairs, a motor and pairs, rolls over your neighbor's dog? What's great for a snack and fits on your back? It's log, log, log. It's log, log. It's big, it's heavy, it's wood. It's log, log. It's better than that, it's good. Everyone wants a log. You're gonna love it long. Come on and get your log. Everyone needs a log.
Log from Blammo.
So for some reason, every time I do logarithms, I think of him, that incredible man, and I really enjoy them so much. I'm looking forward to teaching them to you now. So here we go, logarithms. Let's start with some notation. You might be asking, why logarithms? I thought we were working with exponentials. Well, you'll be happy to know that they are very much related. So let's talk about that. Back way back in the day when you guys were in Algebra 1, you learned about inverses, right? Inverses of each other. So for example, if you used addition, you might have used subtraction to undo addition in a problem and isolate x. Do you remember this? So let's write some of these down. So inverses, right? Inverse properties. You learned about these. If I had addition, you knew that you can switch pretty much back and forth with subtraction. If I had multiplication, you knew again that you can switch back and forth between what? It's like I can hear you talking to me through your computer screen. I know you're probably answering out loud and making everybody think you're weird. I've got multiplication, switching back and forth, division, right? Here we are, we're learning inverses. You remember this, this is Algebra 1. So plus, or addition, sorry, switching back and forth to subtraction, multiplication has this relationship, this tight relationship with division. We even learned some more, how can I say, some more advanced things moving forward, right? Especially when we were learning how to complete the square. We learned things like squares and square roots, right? Those had some sort of inverse thing happening with each other. Well, it just so happens that exponents, wrong color, exponents have a relationship, the same type of relationship that the other guys have, except their relationship is with logarithms. All right, so let's look at some notation of logarithms and see why it is that they're even related to each other. Okay, so let's consider the following example. Let's say I've got, and let me try and stay color coordinated here. I'm going to do 81 equals 9 squared. I think we can all agree on that, right? 81 equals 9 squared. 9 times 9, 81. We've known that since 3rd grade, if not earlier. Some of you guys learned it earlier. Well, logs utilize all that information just kind of in a different order. Okay, now that base number 9, that's still the base in the log. And this time, instead of putting the base of the log as a large number, we're going to put it in the subscript. Okay? And interestingly enough, we say this log base 9. And I made that 9 with a really long stick because I don't want it to look like an A. Okay, so log base 9. Again, let me stay color coordinated here. Okay, So log base 9, which is nice again because we call this 9 a base number, right? Base 9. So cool, that all kind of matches up. And then we've got the 81. This time we've got it over here, which I guess that kind of makes sense. You know, that now 81's in the mix, whereas before it was all by itself. Again, it's this whole idea of inverse. So what do you think is going to go on this side? On the left side. If you're saying 2, I'm happy. Okay, I'm a happy math teacher. 2, that's really all we had left over, right? So these two things, this exponent and then logarithm stuff, they have this tight relationship happening where all the numbers are associated with each other. They kind of show up in both situations. The same way it showed up in both situations of x, the red x squared and the square root x over here on the left. And so what log is really telling us is if I've got a log base 9, what exponent do I need for me to get 81? That's the real question here when we're talking about logarithms. And sometimes they're nice numbers and sometimes they're not so nice numbers. But if I'm thinking of it this way, and if I were to give you another example of this, and I said instead log base 11, and let's say, and again, let me stay color coordinated, log base 11, and then I'll put, let me give you nice numbers at first, right? 121. What do you think that would equal to? Right, so again, what are we asking? We've got log base 11 here, first of all, just to keep with learning how to say these things. Log base 11 and then we've got of 121. So what exponent do I need to tack onto 11 in order to get 121? Now, I know some of you already have the answer, but you know, just to look at it with the math on this on the left side, you know, our inverse happening over here, we've got 11 and we've got the 121, and now we're all wondering what's there, right? We didn't have it. So again, I gave you some easy numbers, so I'm hoping you guys already kind of have an idea. Hopefully you're all saying that the answer is 2 again, right? 11 squared is 121. So that's how logs work, you know, it's just taking information and it's trying to kind of puzzle out, what should I have had as an exponent in order to get this red number here, this whole number. Let's try another example. I'm going to test you a little bit. Let's see something that's a little more complex. So this time I'm going to do log, and then I'll do log base, let's do 2. Okay, so again, that's log, I'm just trying to reinforce vocabulary here. Log base 2. And this time I'm going to find log base 2 of, let's do 16. Or you know what, let's do 32. That one's more fun. 32. Log base 2 of 32. Now, again, sometimes when we see numbers, we start doing things like dividing, and we start doing things like multiplying, or you know, stuff like that. So if you're thinking 16, we're not going for that, right? We're looking for exponents here. So to kind of write out the inverse of this, we've got 2. And we've got 32, and now we are wondering with great distress, what exponent do I need there to achieve 32, right? 2 to the what power gives me 32. And so, you know, we can sit here and think a bit, and some of you who are really savvy with your exponents, you might already have an answer for us. And really, if I'm stuck, I could always just start multiplying 2's, right? So what's 2 times 2? Well, that's 4, so that wasn't enough. How about another 2? That's 8. Still pretty low. Another 2, we've got 16. Getting closer. And another 2, that's 32. Yay, we found it. So how many 2's did I need to achieve 32? I needed 5. So that is my answer for this logarithm. Okay, so now when we look at logs in the future, we're going to see that it's very typical for a log to be base 10 or base e. Okay, here e comes back to see us as we work with logs, since we saw it with exponentials as well. But just to kind of get a basic idea of how logs are related to exponents, here is a few examples of how those numbers are very, very intertwined as we discuss them as inverses. Okay, so that's the makeup of a log function. So to continue, let's go ahead and talk log, what it looks like as a graph. Okay, we're going to continue with log as a graph. All right, so let's talk about log functions, all right? And I've got a picture here with a combination graph, right? And it's perfect because it's showing that logarithmic functions are the inverse of exponential functions. So I like this picture a lot. I didn't make it. MathBits made it, but here it is. And this one's log base 2. Okay, and as we can see, just like as before, the base 2 here is the same as the base number for the exponential function. We've got 2x. And then now this time, of course, remember that they're inverses, so they swap the x and the y and all that kind of stuff happens. So it's kind of weird to see the x in the exponent for the blue function, and then the x as part of the log function in red. But again, remember, the domain and ranges change, so we have to keep that in mind. So let's stay color coordinated, and before we get into log functions, let's talk exponential functions. So let me erase this. Let's talk about these individually. So we've got the exponential function. And let's check out domain and range. And we've already gone over this, but just as a recap, and to emphasize that they are inverses of each other, we've got domain of exponential, and again, that's our x values, right? And if we look carefully at this graph, and another reason why I like this graph is it's really clear to see that that function is going to keep getting, wide on the right, so it's going to continue to grow in the positive direction, although it doesn't go in the positive direction very quickly because it starts to angle up pretty high, but it's still headed in that direction. It might take it a while, but it'll still head there. And it's also very clear that it is heading in the negative direction without any problem at all, right? So we can go ahead and say that domain is all real numbers, and we're going to go ahead and use interval notation or set notation here and write negative infinity to infinity for my domain. Now for my range, something a little different was happening for my range here. If you remember from the video on exponential functions, we knew that it had an asymptote, a horizontal one to be precise, at the line y equals 0, or the x-axis in other words. And we knew this was the case because we realized that, what can we put in for the x value in order to make our function negative? And in the last video, really many of us realized, well, we can't, it's impossible. Even if the exponent's negative, we don't get negative numbers. It'll never be negative unless we shift the whole thing down, and that's not what's happening. So it's safe for us to say that not only will this function never be 0, but it'll also never be negative, and so I can write my range as such. Now, given that logarithmic function is the inverse of the exponential function, we should just be able to swap my domain and range. But, just to go over it step by step and make sure that everybody is seeing where these are actually coming from and not just blindly accepting rules for what they are, let's go ahead and go over domain and range individually so we can prove that the domain and range is in fact swapped. So let's look at the red function now, logarithmic. Again, we're going to focus on the x values, right? And so we're looking at our graph, and we kind of have an idea about how asymptotes work. I can tell that this function is, going to continue going upwards very slowly, but it's going to go upward. I can also see that it's going downward, so that's nice. But let's start with domain. Domain is our values of x. And so looking at this arrow down here going straight down, it's looking a lot like the blue arrow that was coming out over here, which was just going, in the negative direction, not crossing the x-axis. So it's safe for us to go ahead and assume that our values of x probably won't cross that axis. Now let's think about what that means. In the other situation we had, or in the previous work, we had logarithms, right? We were comparing them to exponents. So, we have some logarithm, and I was using blue for the base. So we have some logarithm base a for some value up here. We're going to go ahead and call it x. And it's going to equal y. So let's think about this in terms of numbers, and again, when I have all those letters, that means a to the y equals x. Okay, and again, that was just what we determined from the last part about, inverses. So let's think about this. What exponent would make x negative? Hopefully you're thinking about it and thinking, well, exponents really, as long as a is positive, it's making all my numbers positive. It wasn't really possible before to have an exponent that would make negative numbers, right? We already agreed on that with the blue function. So the answer to this is never, right? That never happens. There is no exponent that would yield a negative number from a positive one. That just doesn't happen. Okay, so no negative x's, that's fine. How about 0? What exponent of a would yield a 0 as the output? And again, hopefully you guys are answering nothing. Even if I put 0 in the exponent that equals 1, we had this whole conversation in the exponential video, which is kind of why I'm kind of trying to get through this logarithm stuff. I'm sorry, I apologize if I'm going kind of fast. If you missed the exponential video, I really think it would benefit you to stop and go back and watch that one first. But back to this, a to the what power gives me 0? Nothing. Again, this never happens. So again, we have the situation where we don't have negatives and we don't have 0, and we end up with the vertical asymptote here, which we remember from, if we remember from rational functions, that's a very strict asymptote, right? So going back to our domain then, we can safely say, now that we've kind of, in a way, proven it to ourselves that we can't have negatives and we can't have a 0, we can go ahead and now give the domain as 0 to infinity. All the positive numbers are fine, but just not 0, and of course nothing negative. Now how about the range? We can make assumptions, right, because we already agreed they're inverses, but again, looking at the function, this guy's going up slowly, but it's going up, and over here at the bottom it is definitely going down. So for our y values, we can go ahead and say that we'll get all values of y, right? We can get all sorts of answers. And if we think about how log works and what y is, can I plug in positive numbers? Sure can. I can plug in positive exponents. What happens if I plug in fraction exponents? Yeah, that's okay. You guys can work with those in your calculator too. They're not very fun to deal with, but they're doable, right? And how about negative numbers? You guys might get stressed out by negative numbers, but if you remember from our work with exponents, then you know that negative numbers just turn things into reciprocals, right? We turn to the reciprocal. Reciprocal takes care of negative exponents. So with that being said, we can go ahead and happily say that the range can be all real numbers, or negative infinity to infinity. And so we have justified with our picture and with a little bit of math thinking that exponentials and logarithms, not only are they inverses because we can see that they are a reflection across the line y equals x, but we also see that their domain and range are opposite of each other. So inverse functions very helpful as we continue to make this relationship between exponents and logs. And so as you continue on with your work for logs, here are a few things to keep in mind now that you've gotten a chance to see where they come from, in a sense, and see what they look like on a coordinate plane. There's a few things that you'll want to add to your notes maybe as you practice with your homework, as we move on to tackle some word problems. Here are some things to remember. First of all, it is a function, which means we can continue to apply transformations to this function just the way we did with exponentials and all the functions we practiced with before now. Okay, so what do I mean when I say that? When I say that, I mean that y equals, it is possible that you may see a stretch, okay? Nothing really happens to a, so we don't have to worry about that. Ooh, that's kind of weird because you have 2-letter A's. The rainbow A is the stretch, okay? Let's make the stretch. Okay, it is also possible that you will see a horizontal translation. Okay, so keep those in mind. Those still happen, and a lot of you guys like to keep that idea of moving them opposite, but which is fine as a shortcut. But just remember, the formula has a minus sign in it. So if it's a plus sign, that means that h is negative, so we're moving to the left. If there's a minus sign in there, that meant that h was positive, so we're moving to the right. Again, this is all old transformation stuff, so hopefully this is ringing a bell, but that is a horizontal translation. Okay, and then of course, we've got plus k, where k is a vertical translation. And that one was a little easier to deal with if you guys remember. If it's positive, you move up. If it's negative, you move down. So not too bad. And sorry, just to fix my notation a little bit, this x minus h is looking a little floaty. This is part of log on the same line. And we've got x minus h. Okay, so be on the lookout for transformations on the logarithmic function. You will see it in your homework, and it works the same as all the rest. It's just now we're dealing with a different shape of function where it kind of levels out. Okay, starts sharp and levels out, whereas the exponential started kind of level and then gets sharp. So that's pretty much it. We're just moving this function around now rather than the other one. Okay? This is my log function. Okay? Just different shape, but same old thing. Another thing for you to be aware of as you're working through your homework is that oftentimes when they're writing notation for log, they don't write the base. So let's see what that looks like. So occasionally you might see this. And you might be wondering, where's A? If you're not wondering where's A, you should be wondering where's A. Now, where's A? In mathematics, when we write functions like this for log, if they don't write A, we can assume that A equals 10. So the same thing goes for your calculator. If you've got log on your calculator, but there is no base, it's just the word log, you can go ahead and assume that your calculator is referring to the log base 10. Base 10 is a real common base for logarithmic functions. So instead of writing it every time, anything to make our jobs easier. I mean, math is already challenging enough, right? Don't write 10. We don't write 10. So I don't know if that makes it easier or more confusing, but whatever the case may be, you will see it in your textbook without a base number. And now we know, if I don't see a base number, I'm going to assume 10. Okay? Otherwise, on your calculators, if you have the calculator that's just a hand calculator, it usually will say log base x, y, and you can punch in the numbers depending on which calculator you're using. Okay? In the same sense, you may also see this one. Y equals ln x. And so now you might be asking, where's A? And what on earth is ln? Oh, I can't write and talk at the same time. And what is ln? It's usually written with a lowercase l, but I suppose I should write it as an uppercase L so it doesn't look like the number 1. ln. So here's the answer to those very great questions that you've just asked me. A, in this one, well, let's start with the question of what is ln, right? What on earth is ln? ln is the natural log. Okay, so in the video about exponentials, we talked about e, e being the irrational number that usually is associated with things happening naturally, not necessarily in nature, but things that happen in real life. So, you know, that's money. When we talked about compounding continuously, it could be used to refer to biological processes like the growth of populations, bacteria, viruses, so on and so forth. So natural log, we're going to be using E because it's natural. And so that kind of helps us answer where's A. And again, that looks like a weird sentence, but remember that E is irrational number, kind of like pi, that is equal to a forever decimal, but we can go ahead and stick with 2.17. I guess I should put a few more decimal places. So again, where's A and what is ln? ln is a natural log, so just basically another way of saying log. And A, we can assume this time, since it's natural, we're going to assume the base is that natural irrational number E. So to rewrite these in a way that, so we don't forget, again, this time the base is 10. And over here, natural log is really log base E, which is not a variable. I'm sorry, I sound like a broken record. It's not a variable, it is an irrational number. And then of x. Okay, and so for today's homework assignment, hopefully these notes continue to support you, and I hope that you're writing some of them down as you carefully watch along with me. Your homework tonight is going to be another 5 problems. I believe this one's homework 11, and you will be practicing with the transformations on the log function, graphing a log function, and that sort of thing. So in our next video, we'll be looking at some log properties, just as we did with the properties of exponents. And again, we'll be able to see how those two things are related and why they're so necessary to learn together. So hope this helps. I hope that it was informative. I tried my best to stay color coordinated. I have very much been appreciating your constructive criticism, your feedback about the videos and what you need from me. It helps me cater my videos to you as a class. So please continue to do that. Again, I applaud my pre-calculus class for doing such an amazing job of getting your assignments done, of taking your quizzes, of doing them enough times until you get 100%. I commend you. I'm proud of you for trying so hard to learn, even though times are difficult. So please keep doing that. I look forward to hearing from you. You know where to reach me if you have any questions or comments. And continue staying safe, and I'll talk to you guys next time. Bye-bye.